Hello everyone, it's July 26th, and it is time for the libembeddedhal meeting. Alright, so the agenda for today, I'm going to go over the progress report of iteration 8. I'm going to talk about some of the chores that I've been doing, just a lot of cleanup everywhere. The experimental directory and namespace, I'll talk about that and what it is. I'll update you guys on the new document configuration and API theme. The planned alpha launch interface review, which is actually ongoing, so it's actually starting up now. Compile time validation and factory functions, which is going to be pretty nice to see how we pattern that out. Just kind of see an example, very small example. And then finally, probably the big part of this entire conversation, this entire discussion for today, this entire meeting is going to be this last part, which is starting a journey into safety critical floats. I am taking something that I've been working on for the last 6 months, I think, and we're going to kind of revert all of that. So, see how that goes. So first off, let's take a look at alpha launch. So we got a lot done this iteration, so I'm really happy with everyone. Thank you everyone for having put all the effort in. Davi got closest working, which is awesome. Got map in. I'll be discussing that a little later. Sarah got 5 different things in. Although this, I'm sorry, four CLs in. The last one here we decided to remove because it wasn't really necessary or useful. So until we find a need for inverted masks, we're not going to have them. Leah got mock servo as well as generic RC servo in, so that's great. I think I must have landed this at the beginning of the iteration, because then that's what kind of allowed Malia to be able to make her. So there's kind of a waterfall connection between me getting this done and her getting that done. How to use libembeddedhal without Conan. This is actually already without Conan. Yeah, I think I just added this blurb for that. And then finally, make percent from ratio safety critical. So just have to redesign it to make sure that it never has an overflow condition. So those are what we've done so far. For next following week, we have getting I2C probe. It just basically tells you whether or not there is a device on the other side. Poll, which is a way to poll a particular function until it returns back true. A couple more, the final set of unit testing stuff. Minimum speed I2C. The point of this is that when you have a whole bunch of different devices that are talking over I2C, if some of them can talk faster, the protocol we want to have for drivers in general is that if you can talk at a certain speed, just set your speed to that amount. And yeah, just set it to that amount. No other work needs to be done. No need to don't take in any parameters for it. Just simply set it to your maximum. What this particular class does is when you pass this particular implementation of I2C over to all the other drivers, what it does, it tracks whatever the smallest speed was that it was given, and it sets and configures that device to that speed. If you ever wanted to set it to a particular speed, then you could just set it directly as long as it's lower than everything else. If anything else is lower, then you're going to need to have that speed be lowered. So that's the benefit of minimum speed I2C. Makes it such that you don't have to worry about making sure that everything on the same bus is at the same speed. It'll force it to be that way. After that, we have bitbang SPI, which Liz should be finishing up. Alpha launch review, and then make RC servo an example device driver. Although I might push some things out another iteration just because of the fact that there's going to be some little bit things shaken up in the code base. So yeah, but notice how we don't have any iteration 10 or 11 here. 11 is supposed to be our final launch. That's going to give us like another month of extra time, but we're getting really close to the end here. We're pretty much ahead of schedule. I firmly believe that we can actually probably get a lot of things figured out by the end of this iteration. I'm going to be putting in a lot of effort to make sure that happens. So hopefully we get it out by August 9th. And yeah, get towards our final bits of review and then put it on Conan. Any questions so far about the alpha launch schedule and assignments? Cool. Let's get back into it. All right, so me doing some chores. Let's look at the chores that I did. Let's see. Let's go up to the top here. Just gonna go over a couple of these, some of the commits that were put in by me. There weren't any issues associated with them. Let me go back out of this one. Let's go commits. So doing some migration over to std error code. There's There's a lot of cases where error code is sufficient. So if they are sufficient, then we should just use it. Rather than making our own types, there's a cost that you get from using like extra types per each error type. So if you could just use error code, that's going to be fine. I do want to, error code doesn't give you a lot of description of what's happening though. So hopefully we can get stack traces worked out. That's another topic though, so not going to worry about that too much. Moving some other things to factory scheme, just kind of cleaning up some things here and there. And I basically just ran through a whole bunch of issues. I think we were at 56 before. I kind of killed off 10 of them. Just kind of getting rid of any sort of things that just didn't make sense anymore or shouldn't be around, because we either already covered them and we forgot to, we may have forgotten to resolve those after a PR was put in, or so on and so forth. So there's a lot of stuff that's been changed up. I'd say one of the bigger ones is just some changes to integral distance and some changes to to frequency, making it into a POD, plain old data struct. So you can put it into template parameters, that kind of thing. But you can always look through these again to get an idea of what has been happened here. So a lot of just cleanup. So our issue count has gone down quite a bit. All right, and now on to the rest of the real presentation. So next up, we have experimental directory and namespace. So a lot of the drivers that use units, we decided to kind of postpone for the alpha launch. So I didn't want to get rid of them or delete them or kind of remove them from everywhere else. I kind of wanted them to still be there. And I know that C++ and GCC and Clang and other compilers and a lot of systems will have an experimental folder where you can find your interfaces that are still in limbo. So you can test them out, play with them, see how they work, that kind of thing. Or even get ahead of the development cycle so you can get everything working with it. And yeah. So we have this new directory. It's inside of libembeddedhal, the include directory for that, and it's called experimental. Any interface or library that's not ready to be committed, a committed API will be placed in there, and we'll continue to investigate it and experiment with it until we feel like it's in a good place to be moved into the interface of everyone else. Obviously, all the other interfaces are still under debate and under investigation, but those are the ones that are for alpha launch, so that's why they're getting an exception. That's why they're not all placed into the experimental directory. Any questions on that? All right. Next up, updates to Doxygen configuration and API theme. So yet another change to documentation. And in this case, I made Doxygen more permissive to pull in as many things as possible. I am concerned that I think it might be skipping documentation right now, just because it can grab as much information as possible and doesn't want to warn you if you haven't documented something. So I'm going to do some checks on that at some later time, but that's something that's happened. mkdocs has been removed completely. It was a system we were using before. That's just been removed because it was more complicated, more than what we really needed, and we didn't need a multi-page, super fancy wiki type thing, because we already kind of have that in GitHub wikis. And I don't think we really need to go all out and be super duper colorful in our own little like mkdocs. So we can remove a lot of code and remove a lot of dependency on like having to maintain all that by just eliminating it, and also reducing a lot of complexity. Wikidocs should be more than enough for what we're doing. API docs are done solely through Doxygen, along with new Doxygen theme. I'll show you that in a sec. Documentation for libembeddedhal will exist on the front page, and all other more detailed stuff like using floating point versus fixed point, or how to use a serial driver, embed serial in drivers. Those will all be placed in the wiki page. So when you want to explain, we want to actually have design docs to explain GPIO and why we chose what we chose, and same thing for every other interface, we will put those into the wiki. And actually to show you what the new Doxygen theme looks like, we can take a look here. So if you just click on this link here, it'll take you to the documentation. It also has a dark mode and a light mode. Sorry if I kind of blinded you there. Yeah, and then we have some modules here to kind of put things into certain groups. So all the utilities are under here. So enumeration, literals, bit width, duty cycle, frequency, map range, overflow type, that kind of stuff. And then also testing stuff as well. All right, so that's that. Actually, I'm just gonna stay out here because I'm gonna have to click around to other things as well. So planned alpha launch review. So I've been saying that a couple times. The whole point of the alpha launch review is to just look through every single one of the interfaces and scrutinize them. figure out if there's something about how they're designed that just doesn't make sense or cannot work in certain situations. And then once you think about an edge case that does exist, it's really important that you also consider how the current API can make that particular interface or that particular situation work. Because you'd be surprised, and it may not be the nicest solution, but you may be surprised what solutions you come up with, because I'm going to show you one example how I thought there was an edge case that needed to be fixed. And then as I went through the process of thinking about that edge case, I realized that that solution just can actually be redone with the code we currently have. And then it turns into a case of like judging the cost of adding a new API versus keeping the current API. And here's the discussion page down here. It's very different. If you haven't seen this before, it's really interesting. It's pretty new to GitHub, and I really love it. So if I just actually click on here, so we have issues, pull requests, and we have discussions. The wiki page is over here. These are a whole bunch of test ones that I put together. So it's like an actual forum. So you can click on this one. The two participants are just me and Davi. And we have this list of things that we need to check off to make sure things are good. And the one I want to go into specifically is attach, interrupt, or capacity. So one of the ideas that I had was, okay, well, we need to use Serial with the ESP8266 to do Wi-Fi stuff, be a Wi-Fi client. Great, fantastic. But, I know that having like a buffer of 1 byte is probably not going to work out very well. So what if I just scrutinize the actual interface? Say, hey, all Serial devices have to be buffered, so they have to be able to tell me what the capacity is. So I can just ask them, hey, is your capacity big enough? And if they tell me, no, we only have 5 bytes, I'm like, yeah, you won't work. I need at least 1K. But then I'm thinking to myself, who makes the decision on that? That seems too much of a decision. Like how do we calculate 1K? And you can do a lot of different modeling to see, why 1K works. Maybe we want to do 1.4K because that's the size of the maximum packet size for an ESP8266. Or maybe we want to double that so that you can, as you get one of them and you pull that information out, you can get a second packet. These are ideas that you can come up with. The problem is each one of these kind of asserts a certain thing about the application. So I didn't really like capacity so much, but I was like, okay, maybe that's fine. And that's why I thought, well, maybe what I really want to do is I'm just afraid. What am I afraid of with Serial, with UART? I'm afraid that when we start gathering more data, as the data gets sent over to us, because it's asynchronous, as data gets sent over to us, our internal buffers will fill up. And when they fill up completely, we're going to start losing data. So why not attach an interrupt to that Serial driver such that whenever it fills up, you call it and it dumps all the data out. Or when it's like halfway, you can provide a percentage. You get some percentage of full, you go in, you grab that data out, boom, done, no issue. ESP library can just simply add a callback so when that ever happens, it just dumps the data out. Problem. So most likely that happens is going to be an interrupt context, because the thing that told you that the thing was that particular buffer was up to a certain fill rate is going to either be the interrupt you're using for pulling the data out of the FIFO from the UART, or it's going to come from the DMA driver that's actually pulling data out from the serial port onto your RAM, into your buffer. So we can end up having a very, very large amount of data being copied in an interrupt context. That's not going to be very good. Then I started thinking to myself, what makes more sense? Does it make more sense? Well, how do we make this work normally? Well, normally you'd have to, if you have a reasonably large buffer, you still have to check every so often. If you have a very small buffer, you have to check more often. But let's say you can't check more often because you have a lot of work you have to do. Well, that means you have to make a bigger buffer so that you have more data you can stream out, or you can accumulate more memory, more data before you have to, check it every single time. So I thought to myself, I guess in that case, you just have another thread that's checking on the ESP, making sure it's doing its thing. And as long as you check it fast enough, you don't have to really worry about this problem. So that seems pretty good. But what happens if you don't check it fast enough and your thread gets blocked for whatever reason? Well, then you want that interrupt, don't you? Well, now we have to think about this idea of if that interrupt gets called and it pulls data out, that interrupt is now working above all other tasks because it's an interrupt. Its priority has to be above all other tasks. So basically, it's like you promoted the priority of that particular interrupt or that particular task up to the maximum above everyone else. And here's where lies the rub. What did you really get out of this? Because you could have just simply made the task higher priority. You could have decided to make sure the other code didn't run as much, so you had more time to run this other code, basically allowing it to run faster. Or you could have given it more RAM. But what you really did was when you added the interrupt, you just simply made it so that it got called more often. Because now, rather than calling when you have the time allotted for you, you call when the time is allotted for you and when it's not allotted for you, whenever. And that seems like consistently a bad choice in design. So that's where I realized that attached interrupt is actually a bad choice going forward. May seem like a good idea, but really the real solution here is to check more or give a bigger buffer. Check more often and give a bigger buffer. That's pretty much it. Yeah, that's it. I was gonna think if there's a third one, but no, there really is just those two. So that means that this particular API addition doesn't make any sense because it would cost more than just having the API overall, and would do the same thing as simply modifying the code slightly. So that would be an example of taking a problem that you consider and coming up with a thing that could change the API that would allow a fix for it, then trying to use the current API to figure out how to like how you'd go about implementing that particular problem. And if there's no way to do so, no way at all, then it should be put in. If there is, compare the two options to see which ones are better and really give the other one a fair shake. Because I was really hyped about attach interrupt until I started thinking about it more and more, and eventually it turned into this case where it didn't make any sense. So that's what the alpha launch interface review is supposed to be like. And you can see the little discussions that I have with myself, along with also with Davi here and there. Some of these are discussions I've actually had with other people, but I'm just I'm listing out all the things that we kind of found from there. So just get an idea. If you see me talking to myself, it's some part me talking to myself in this discussion, but also discussions that I had offline that I'm just writing down.
So which solution are you going with? Like just pinging it more to give an indicator of how much memory you have left, or increasing the buffer?
It is up to the user. It's up to what they can spare. If they have more memory, I'd say it depends. It really depends on what they're doing. They want to save more, like not wake up as often, and they want to power save more often, and they want to, in that case, and they have more RAM available, they should just up their buffer. If
it's not our design choice either.
Yeah, exactly. By doing this is like, so the thing about a lot of these APIs is that like, the good question though, is that like we want to make sure that the other person has as much options as possible. Adding attached interrupt in a way gives more options to the driver, but actually gives less options for the developer themselves, because now the developer has to deal with the fact that this library out of nowhere has to now take full control over the system and hold it in that state and have the design around that. Whereas if we go without it, we don't have to pay that cost. So right now, it's simply we give the control back to the user and we tell them, here are your two options on how to make it better for your system. Give your thing more time or give it more memory. Or both, if you need both. Sometimes you may just need both. Did I answer your question?
Yeah. Perfect, thank you.
Cool. Any other questions? Cool. All right. So next up, that's how much time we have. 20 minutes only. Okay, cool. Compile time validation in factory functions. Let's check it out. That's too hard to read, but if you look at the docs, you can kind of look at it, but we can just go over to real code. Here we are. So might look a little complicated with the template stuff. Basically, we have a couple numbers here: frequency, minimum, and maximum microseconds. If need be, we could have an RC servo library that doesn't have, has these as runtime variables. But here's the thing: when you have a servo, it's almost always going to have a well-defined frequency and a well-defined minimum microseconds and a well-defined max microseconds. So having them as template parameters at compile time, like numbers at compile time, seems perfectly fine. Here we can actually check to see if they even make sense, because if the min is less than hold on, minimum. Oh yeah. So min has to be less than max. Yeah, and that works. And the frequency needs to be this, like 1,000 over the frequency needs to be greater than this value here, just to make sure that the frequency does not exceed or does not go below the maximum microseconds rate. And then that's basically our compile time checks, where we don't even have to do any runtime checks at all. And then here we do our final work. And really it's just this line here that does a check to make sure configure works, a little bit of computation, and then finally you construct the actual object and you return it. And this is just creating a temporary filling it up with these things, and then returning it by move constructor. So that's kind of how this works. This one's a bit complicated. We'll probably have some other ones in the future that we'll show off here. But that's the idea. So compile time checks, configure the device as you would if you were doing it in a constructor but needed to emit an error, and then do the last steps in order to return the object. And with this particular pattern, we can more easily do compile time checks because the only thing that's templated is the factory function. Otherwise, you'd have to actually go back to this real quick. You'd have to template the entire class in order to get a template on the constructor. Because even though you can put templates on constructors, you can't actually use them. They have to be implicitly interpreted. That's a complicated thing. We don't have to worry about that too much. But putting the template on this class here results in code bloat. So we want to kind of be careful about whenever we make a class templated. Because you'll effectively have a new version for every frequency, min, and max value that can be separate from each other, each unique variant of that. So that's why we don't put them here. Really helpful to put them here. Any questions on the factory functions? Cool. Alrighty. Now for the part, okay, cool, we're making good time. Now for the part about the journey into safety critical floats. Yeah, so just start off, y'all all know that for the longest time, I've been harping on the idea that we need to use fixed point for everything because it'll have a bunch of benefits for us. Basically, you'll be able to get fast computation on your integers. Even if you don't have an FPU, you'll still be fast. You'll still be great. If you have an FPU, probably won't be able to use it, but hey, all your code's faster, right? If as long as it's all doing fixed point arithmetic, it should be fast. So you're just getting the best of all worlds. You don't even need all that hardware. You can even simplify your CPU down. Yeah, no, that was a mistake. Let me explain. So a few days ago, I spent a few days implementing embed map using integer math. That was probably one of the, I don't think it was the hardest problem I've had to solve when it came to integer math, but it was the one that annoyed me the most. So I made sure that the result will never return an error. And by that I mean it can return an error if you have an invalid input for the map function, which is only one condition that can happen. But otherwise, there would be no overflow errors. There'll be no approximation errors. It'll be as close as you can possibly get it using just integers. I wrote a soft proof in the comments to explain how every step works as per AutoSAR guidelines that you must comment how you did your math. And then I made tests and submitted code. And after all of this, I felt exhausted by doing all this. It was a lot of work to try and do this. To give you an idea, let's look at the map function to get an idea of how much is required in there. So map function, create this little map range guy. This is the little function. This is fun enough. This is an affine transformation. That's what map really does. That's what it's called. And y equals mx plus b is also another variant of an affine transformation. Just a little fun fact there. All right, so here we have our target. We have our range for input. We have a range for output. First things first, find the distance between the input and output range because we're going to need to compare those, make sure they're not 0. So if the output range is 0, it just means that and just to give you an idea, if you haven't used map in Arduino or something like that, it basically takes some number in some range. Let's say you have the number 0 to 10 and you have 5. Oh, actually I have this example here. And your output range should be 100 to 200. What you're going to do is you're going to map this value between this range into this range. So if this thing's halfway between these two numbers, the result should be halfway between these two numbers. And yeah. So that's really cool. It's really helpful. Really awesome functionality. So the thing is, if your output distance is 0, meaning that the start and end are the same, that means all inputs basically map to the same point. Okay, so just return one of them, x. That's fine. If the input distance is 0, so the input range is the same number, then return invalid argument because you can't map something that's one-dimensional to a two-dimensional space. You can map 1D down, but you can't map 1D up. And I bet there's some weird mathematics that actually says that you can do that, but this doesn't really make sense for our use case. This is the only reason why there's a boost leaf result error or a boost leaf error here. Otherwise, without that, this entire thing would work without any sort of errors being coming out. So we do some clamping. We do some math that's akin to doing FOIL, splitting up a number by its whole number and its percentage value, and then doing some arithmetic with that, explaining every step of the way how these things ensure that there's actually never going to be an overflow because we already did bounce checking up here. And then finally you take the quotient and you multiply it by your other value, and then you take your remainder and you multiply it by your percentage value, then you add those together and that gives you your whole number again. Then you add your offset, then you're done. And then I think the main thing is I had this thing all done, but coming up with the explanation for certain parts was kind of rough a bit. And I had to think about, is there any situation in which any of these numbers after this point, given these properties found above this point, where they would fail? And I don't think I gave a good enough proof to explain that they would not fail. I kind of just assert that they won't. But yeah, so that's kind of how that went. Funny enough, even with all my different unit tests and checks, I think I got something wrong still, because RC Servo has to do some wackiness in order to get map to work, which just made me even more upset about the whole integer math thing. So, I mean, it's not like I have to not deal with that otherwise, but I decided to start looking for some relief in pre-made fixed point libraries to make the experience a little bit easier. Because after all this things I did before, I really would have loved if I could just do all the math and then just bounds check it. And if it's fine at the bounds check, then I go, hey, invalid value or whatever. I still probably need to check this one here. But at least I can just do a bounds check at the end and be good to go. That'd be great. So the idea is use an auto-promoting fixed point library, then do bounds check at the end. We'll be fine. Cool. Let's see what happens. So step 2 is I start looking for a few libraries. I was talking to Milo about this along with some other people about like how CNL, I bet it's really awesome to I bet it has a lot of really cool properties, but I just can't figure out how to use it. I feel like the documentation isn't fully put together, and it's the most popular one. And I've actually kind of gone back to it multiple times to see if I can just, yeet all of my current code and just use their code. But every time I go to it, I get confused. I don't fully understand how to use it. I eventually get a way to use it, but I don't know how to explain it to other people in general. So that becomes a bit of an issue. And then I find FPM. Seems pretty fine. It looks pretty good. But then I look at the performance chart. Oh, neat. And that's when the problems start, because they check out FPM, libfixmath, and CNL, and they compare them to native floating point operations on their i7, this device, this Intel i7. And when you look at this graph, whoops daisy, I don't want that. I want to image a new tab. Let's zoom in on this a bit. Yeah, so as you can tell, these ones obviously beat, float and double in terms of add, subtract. Fantastic, great. Multiply. No, we don't win here. Okay, all right, so we lose a little bit. Divide, we don't win here either. What is this one? CNL, fix 1616. It's better than double. It's worse than float though, okay. And then you can see that it gets a bit worse. And then, CNL just drops off completely. And so does fix 16. And now they're gone. And then comes back sometimes. And then they come back a little bit, but then they're also gone everywhere else. And oh boy, look at all of that. Let me check again. Well, actually, that green one's double. So, FPM looks a little better in some cases for power. Okay. But then you just see everywhere else, it just looks like float and everything else just works so much better. This one seems like a weird result. But overall, it looks like the other tools are just not as good. They're just not good. And it kind of blew my mind. I was like, why is the performance so awful? Wasn't sure. So I thought that maybe just because these things had floating point units and double floating point units, that of course, these will be awful because you're doing something that you don't need to when you're on these systems. Sure. But it did make me think a little bit further. Why is the performance so awful? And this is where I started going down a rabbit hole. And I'm not sure why I didn't find this out before when I was investigating this stuff originally, but I eventually found these articles by Richard Harris. I actually found more. I just don't the link that I got from it had it said like, oh, token broken, therefore you can't look at this thing. Find the original page and then click on it again. So I should have saved the PDF, honestly, or at least remembered where I got it from. But there are other articles that talk about fixed point versus floating point and all the different issues with it. But Richard Harris does a fantastic job of going really deep into this stuff. Checking time. Cool. So the first one goes by as you're going to have to think. Basically talking about how when you do arithmetic with floats, you're going to have to think about it. And then he talks about after this, I assume he got a lot of comments from people saying, oh, well, you're doing it with floats, but what you really need to be doing is using fixed point or rationals or computer algebra or interval. And this guy explains in detail why fixed point won't cure your floating point blues. Whatever problems you have with floating point, fixed point's not going to fix it. And literally just writes up an entire implementation, every little bit in here. Talks about some of the advantages of using it. Talks about some of the disadvantages, arbitrary precision, and all this big stuff. All this stuff. I think he uses a vector for big num. He does not try to compare the full-on complexity of how long it takes to the performance of this or the size constraints, but you can kind of tell by what's required to make everything happen here that this is a bit more involved than just simply probably using the assembly-made floating point arithmetic libraries that are built into your compiler. That's what I was getting. That's the feeling I was getting. And I think the biggest part here is this last part here, which is, in addition to not particularly being efficient in space or time, which I'll show you guys some documentation that shows that's very true, to represent the maximum double precision IEEE value would take 128 bytes, as opposed to 8 for the former. So unfortunately, arbitrary precision fixed point also seems to be something of a lame duck as far as general purpose arithmetic is concerned. Quack, quack. So this entire document, if you read it all through, can really very much deeply explains why it's just not going to work out very well. But I'm thinking to myself, well, okay. And I look up some other things, and eventually I find another one of his articles. And then I realize he has an entire series of articles, specifically one on rationals. Well, why not simply just use rational numbers? Have some integer on top, some integer on the bottom, and you're good to go. Look at these equations. You don't have to worry about really anything because, here we have A, B, or say A1, A naught, B naught, A1, B1. Adding them together is easy. Multiply these values here, multiply these values here, add them, get this value in the bottom. And as long as you separate them and keep them as integers, you never have to really worry about division here. So you gotta get rid of division in a lot of cases. And look here, same thing. Awesome, it's just multiplication. Here, multiplication. Here, multiplication. It's multiplication. That's easy and fast for all CPUs to do, and it's straightforward. And then you keep going through here, and eventually you figure out that this particular doing this results in some pretty nasty problems. I take it up to you guys to read this documentation to go into what those problems are. But mostly it has to do with the fact that multiplying two integer values has a problem, in the fact that it overflows very easily. It doesn't take much to take two to get a number to overflow. So you get back to the whole overflow issue. So that's not so good. I will not bore you with the other two. Computer algebra was an interesting one to read, and so was interval arithmetic. And yeah, so basically each option of replacing floating point, or at least trying to change up floating point, given a fresh shake and scrutinized for each problem that they have. And the ending of the series has this conclusion of, really, floats are kind of the best thing we got. To represent decimal numbers, real numbers. They are kind of the best we can approximate. And trying to get fixed point to work is not going to happen. So I started investigating. I'm going to remove this. What's required for safety with floats. And not going to lie, I think this might be all we need. There is a way to ask for if you have a divide by zero error, if something that you put in is invalid, if it's inexact, you have an overflow or you have an underflow. You basically have a way to status check when you do any operation if there's anything that went wrong. And if something did go wrong, you can do something about it. You can check it. You can also clear it in order to get rid of the previous exceptions that were found and do work that way. I would say that the one we probably going to want to really bear in mind is divide by zero errors. Although, not going to lie, I don't know if divide by zero is super important unless we need to bounds something. Because then the cool thing about divide by zero with floating point is that it will return back infinity. If you divide by zero with an integer, that should assert a exception, which will basically almost always just crash your system. By default, it'll crash your system. You can have a catch for it. We don't really know what to do at that point. So with float, at least you have a defined answer to when you divide by 0, which is infinity. Inexact is an interesting one. It's really useful if you try to do addition or subtraction, and you can verify if the number that you added dropped off or not. So when you're adding or subtracting whole numbers, this might be the clear-cut one. Invalid means you got like an odd number or something like that, something weird. Overflow, underflow, overflow or underflow. Yeah, these are useful. Although they should almost never happen. Even with normal floats, should never happen. Inexact will almost always happen, and these two should never happen that often either. So really, inexact is going to be our real ticket here. I'm still looking into how to do this. I think I behoove anyone else to look into this as well to see if they have any suggestions on how to do this. AutoSAR 14 for C++ 14 does not have much literature on this, except for just telling you should make sure to document how your code works so that it's and make sure to bounce check your floats, that kind of thing. But that was pretty much where I stopped at, not gonna lie. I didn't go any further. I was trying to think of other things that I investigated, but that was pretty much the biggest one. And I'm gonna be looking for other type of documentation to see what's available here. But here's the thing. I decided to re-crunch the numbers again because I realized something silly about the last time I crunched the numbers for floats. When I looked at my code base for liblpc, I noticed that we had set the float ABI to soft FP, meaning we were using the floating point unit for all the float stuff. So the numbers were kind of incorrect. So I removed that. I made it all soft arithmetic and reran the numbers. I want you to note that the baseline I'm going up against is int 64, not 32. Reason being is that's how we do floating our fixed point math. We're using int 64 in order to be a holder of our numbers that can't be fit inside of 32-bit numbers. So that kind of made our binary size 1,578. As a note, if you just use int32 for all the separate operations, it's only 608 bytes. So you add almost an entire K for adding in operations with int 64. With float, you pay the cost of 2K, basically a delta of 544 bytes to do it. That's not that bad, honestly. Double, just double, you pay about 1.5K. That's a good amount, but you get to reuse it everywhere throughout the code. If you use all of them, 3.4K. It's pretty big. It's quite a bit. Sorry, that's only for float and double. When you try to use everything, int64, float, and double, the cost is 5.8K. And here's just a couple of little insights here. Like if we just only use double, we pretty much save 1,800 bytes. The dramatic con is that when you target chips that only have single precision FPUs, you don't get to use it. Like basically, it's gonna be bad performance. Pro, higher precision, up to 16 digits universally everywhere. If we just say as a standard, libembeddedhal must use double. And this is actually incorrect. Let's see. It can cost either 605 bytes. In comparison, this is actually, this is actually supposed to be 544. I think I did some things around. I changed some things around. Notice that like the comparisons that are done here, there's less than or equals to and stuff like that here, and there's not that for floats, and that's just because equals doesn't make much sense with floats. So the equals versions of it should not really be considered. Okay, so that's just the flash costs. Now you look at the performance costs, and this blew my mind. This actually kind of upset me. So the amount of time it takes to do a double, this amount of cycles. And I feel like I'm having deja vu. I'm pretty sure I did the same exact thing before, so that's why it looks so similar. But now we have a more put together fixed point library. So now we can really look into the benefits and the issues. Double takes around about this amount in the 8 millions. In 8 millions. And these are clock cycles found from using the DWT timer, which is twice the speed of the clock cycles for, I believe it's twice the speed for the clock cycles for the CPU. So double times in 8 million. Using fixed point arithmetic with rounding division and int 64, 4 million cycles. That was pretty surprising. It's not far off from double. It's half of double, which really blew my mind. Then we have soft float, and that is yet again smaller. So just using software created floating point arithmetic is faster than if we had just done a fixed point. So now there's even less of a reason to use a fixed point. What happens if we remove rounding? What if we just say we lose precision? Who cares? It ain't that much different, not gonna lie. A lot of the cost comes in from N64 division and N64 multiplication. Then we say, okay, well, screw 64. Int 32. This will cause a whole variety of problems. This is not suitable. If we do this, we'd have to probably reduce the scale for which we do percentages, just in general. That may be fine, but again, we're kind of far off. And that's with rounding. When you go into hard float, it obviously just wipes the floor. The only thing faster than that is I32 without rounding. But this one will break. This one has problems if we don't reduce the number of bits that is represented by percent. This also won't work unless we reduce the bits for percent from 4 billion, like 4 billion part. I forgot how to say it. I forgot how to do parts per billion, but basically there are a lot of, you can have very good percentages with 4 billion count numbers. 64K isn't that many. So yeah. So at the very least, soft float and hard float are looking like really good champions right now. Whether or not they'll actually have the precision we need to do all of our work, that's to be decided. So what are the conclusions after all of this? And also, you can also look at the code base and like the code that I wrote to do all these checks here to get an idea. But the conclusion about floats is that we're going to be adopting floats going forward. It just makes no sense to stick with what we have here if it's just going to be slower. And it doesn't exactly cost more, but it costs a little bit less. I think that the speed and performance loss and not being able to take advantage of the hardware that you're using is a bigger cost. Oh, and also the code size drops dramatically once you do move over to hard floats. So, like, if you had them, you'd want them. Fixed point isn't sticking around, though, as it's been shown to be costly in space and time. Takes space, uses up too much time. And if you ever can in your code, try to stay away from N64 multiplication division. If you need to use it, just use it. But like, if look at it and go, do I really need to do this? Next up, we have doing map is still not easy. I looked back at the map problem and I realized that the map problem is still not simple. You still need to be very careful about how you choose the order of operations when you do map with floating point numbers. So something to keep in mind. And we still have a lot of decisions to make, such as when and where do you use floats, just floating point, double or float, or whatever. What operations should you check for? Like I said before, addition and subtraction, I feel kind of strongly about those checking for inexact, although that can be kind of a complicated beast to check for. It's a thing to consider. And whether or not we should just use nothing but floats or doubles, or if we should allow it to be a configuration option for the entire libembeddedhal project. Or, and I think this is probably the one closer to what we may do, have it be user dependent. So the user gets to choose. Everything defaults to float because we're doing, obviously embedded stuff. But if the user really wants to use double everywhere, we can try to make it easier for them to do that. But like basically, you can have a acceleration class that allows you to specify what it's doing for how does this math. You can change the precision based off of which unit you use or which type you use. How that's going to really shake out, not sure. If you have any ideas, please post them on the Discord discussion channel, so we can just go over all that stuff. Or if you feel like it's better to discuss it inside of a GitHub discussion, you can also do it there. But yeah, that's pretty much the big. That's pretty much the the big move currently is that floats are coming in. It should make our lives a lot easier when it comes to doing math, but you still have to, think about it. There is no escaping thinking about it. Just is how it's going to be. So yeah, that is pretty much it. I thought I had one other slide, but I guess I do not. And that's pretty much it for today. So are there any questions about anything we've spoken about? Go back to the highlights page. Cool. All right. Thank you for coming.